Yeah, so what my group and really my research over the last sort of 5-10 years and currently is really focused around is looking at ultrafast processes in chemical systems. As a community, we've got generally very good at looking at ultrafast dynamics in a range of particularly photoactive and photochemical systems, so everything from sort of photovoltaic cells and LEDs through to photocatalysts and sort of photoactive biomolecules. But really, we've only been able to look at sort of the 1% of subsystems so far where ultrafast dynamic matter, really these light-driven systems. What the goal of my team is, and what really my research efforts are around, is really opening up the sets of systems that we can look at ultrafast dynamics in, particularly kind of these traditionally non-light-driven systems, but where ultrafast dynamics still matter. So things like batteries, electrocatalysts, fuel cells, systems that are really driving forward the clean energy revolution, where traditionally we haven't been able to probe sort of ultrafast processes, but where they really, really absolutely matter. And so we build lab-based techniques to do this, but also combine them with these sort of facility-type measurements, like at European XFEL, to really try and answer that question. Yeah, so if you have your mobile phone or your electric car, what's the first thing that you might worry about when you take it out? And for me, the first thing I kind of worry about if I go out for a long train journey or take my EV car for long distance is it running out of charge or even kind of heating up or being damaged. And the reason this happens is the way that sort of lithium-ion batteries work is we have these kind of tiny charge particles, these electrons and ions whizzing around them. And if they don't move in the most efficient way possible, if they don't move in the way that we want them to, they can either damage the battery or we can not get the right power capacity out of them. And so what our goal is to be able to actually watch these processes and understand how they happen. But the problem is these processes happen on very, very fast time scales and very short length scales. And so you need a way of being able to do that and being able to look on those sort of nanoscopic length scales and femtosecond time scales. And what European XFEL and the FXE instrument offers uniquely is the ability to be able to do that, to be able to watch these kinds of charged particles on those tiny length scales, make movies of those processes, and also be able to understand how we might control those charge carriers. And it's that unique capability of FXE, in particular in that hard X-ray range, which is very useful for batteries, or particularly useful for looking at battery materials, that we're trying to exploit. So, as I alluded to, we're really undergoing this kind of clean energy revolution, and lithium-ion batteries are one of those key technologies that are going to be driving us forward. But if we really want to push them to the next level, to really reach our clean energy targets, what's been shown is that our current battery technologies are not going to be enough. We can't just simply scale up what we have. And so what we need is to really make a massive step change in the performance of these systems. And what historically has happened is to make these step changes is a step change in our understanding. And that's why really understanding these elementary processes like electron transfer, like ion dynamics in these systems, these ultra-fast building block steps of batteries is so critical. And that's what we're trying to do here.